Welcome to the continuation of dimensional analysis. You know, guys, it's funny because, once you start recording, involuntarily you become a kind of weird about it. Just the idea that you get the camera on you and then you put the video. It's really weird, actually. Well, no. Okay. So let's see where we were last time. So I owe you the end of that example with the, so I won't do this. So anyhow, we were working on that diffusion model with boundary conditions, and we did the dimensional analysis on it, and we ended up um, with two non-dimensional variables describing the PDE. So let's write. Okay, so we're talking about du dt equals d d2u dx2. So that would be the question. When we know that u in 0 and t equals u0 of t. So this is given, okay? And then at infinity, this is 0, okay? So I'm going to call these equations 1, 2, and 3 because we're going to need them later, okay? And then what we assumed, okay, that there is I'm going to use a word I didn't use before, but that's what we're doing all the time. A homogeneous. It's homogeneous because the right hand side is 0. Relation f of x t d u and u naught equals 0. Okay. That encompasses all the information in this problem, where the right-hand side is a non-dimensional or an adimensional quantity. Let's just use this word now, adimensional, okay, quantity, or a-dimensional quantity, if we want to say it in English. In French is a dimension. Okay. Anyhow, so we did the job here, whatever we did. I don't want to go into it again because you have it from last time. And we ended up that we have two, by the Pi-Buckingham theorem, there are two non-dimensional or adimensional variables, okay, that describe the problem, okay, and these are pi 1, that is x over root dt, and pi 2 being u over u naught. Now you can already see that u over u naught, it's velocity over velocity, so the dimensions are gone, right? So now, right, and let's say equation 4, let's call this one 4, is equivalent to some equation of the form f in pi 1, pi 2 equals 0, okay? And which is, so let's say, IE, okay, f in x over root dt and u over u naught equals 0. Yeah. So I just put what is pi 1. I put pi 1 and pi 2 first because they're related to the Buckingham pi theorem, like to see how I'm kind of applying the theorem, but then I'm going back to what they mean, to what they are, if you. All right. So now by expressing this relation, so from this relation, we can kind of deduce that then we can say that u over u naught is some function of x over root dt. Okay, so I'm going to stop here just to make sure that you understand what is going on. So I don't know what little f is. I just assume it exists. Okay, now doing the dimensional analysis and applying the Buckingham Pi theorem, we end up with, oh, this relation 4 that I don't know what it is, but I know it exists, is equivalent to another relation that just includes 2 variables. So from 5, we dropped to 2. That's the gain. Okay, so from 5 variables in the problem, we know that the problem can be described only by 2. Now, these 2 ones are combinations of the 5, okay, in some way, and that's what, you know, we deduced last time. So the first one is x over root dt, and the second one u over u naught. Fine, okay. So equation 4, right, is equivalent to some functional relation in between these however, no, call them the first one and the second one, the pi 1 and pi 2. Now we go further and we say, oh, you know, but if I am cool with algebra, then this means that I can express one as a function of the other, right? It's like this is an implicit relation in between the two pi 1 and pi 2, whereas this is an explicit relation, right? Explicit, let's just write, okay. So now the thing is that I will go further from here to show you that, you know, in this particular problem, because of some little miracle, we can actually solve the PDE. We can solve this original question, right? What is u of x and t? So it's just, you know, something that happens in this problem. So I'm going to continue, right? So here I'm going to write right? So this was the original equation. Okay, I'm going to put it here because it's easier to follow then. Okay, so, you know, we had u of 0t is u naught of t, and you don't have to write this. I just put it there because it's there. Okay, and then we know that u of t, u of x and t, if you, okay, to be precise, it has to be u0 of t times some function that depends on this variable. So that was on the previous page, basically, when I wrote u equals, right? I wrote here u over u naught is g of, right? So this means that u will be u naught times g of. And then on the next page, I'm rewriting this with its arguments in there, right? So there you go. So now what I will do, I will take this expression. So we don't know what G is, right? I repeat this. What we know what is U because this is given. Yeah, okay. So we don't know what is G, but what we can do, we can take this relation, right? This one, and go and run with it in the original equation. So wherever I see U, we're going to put that right-hand side, u naught times g. And we're going to start calculating which is it and what is what, right? Which is which and whatever. So what would be du dt? Oh, du dt would be dB dt of u naught of t g of x over, oh, right, okay. Okay, of this, right? But actually, the initial data was u naught, not u naught of t. U naught was a constant, right? So that was silly of me. So this is not, this is given as constant. Okay, let's just write it there. Okay, good. So everybody wrote it there, yeah? So it's not u naught of t, it's just u of t, a constant, a given constant. So here I'm going to correct this. So this is just u naught is a given constant, And here is just a constant there. There we go. Because if it's not constant, it won't work. Okay. All right, we're given constant. Okay. So here is just the U naught. There you go. Good. All right. Yeah, everybody with me? There. Good. Okay. So I'm doing here the derivation, right? So U naught is a constant, and then I have to do the chain rule, right? So it will be U naught G prime of X over root dt times dB dt, or if you want the partial, that would be more appropriate to put the partial T of X over root dt. Now, I do remind you how to do the derivative of 1 over X root dt. Okay, I won't do that into, okay, so it's whatever it is, right? So when we do here the algebra, right, X and D are the constants when we do this kind of partial, and then we have to do derivative of T at minus a half, and we end up with 1 over 2 with a minus, and then T at minus 3/2, yeah? There we go. Okay. And now I'm gonna do du2 at dx2, right? So we will have to do db at dx2, d2 at dx2 of the same quantity. Now, okay, you can do it, blah, blah, blah. Okay, I really won't do it for you, this one. So we end up with u naught 1 over dt, the second derivative of g as computed in this thing. Again, is by chain, yeah? Okay. So it's just derivation there, like plain vanilla. Okay, good. And now we're gonna take these two guys, this one and this one, right? Remember that this is du dt and this is du dx2, and run it with it in equation 1. Okay, so this was 1 from the other page. That's 2 and that's 3. Okay, so blah, blah, blah into 1. Okay, so what do we get? When we substitute in there, we end up with, so the left-hand side, du dt, is u naught g prime of x over root dt, right? So I'm just putting the stuff in there, times minus a half x over root d t at minus 3 over 2 equals, now the right-hand side, u naught 1 over dt g second of. So this is just calculation, right? I know you love calculations because it's clear what you have to do. So there you go. Okay. And now we're going to assume that this constant u naught is not 0. Okay. Because by the way, if it's 0, the solution will be just 0 everywhere, right? If u naught is 0, then everything is 0, right? So, and it verifies, right? So we're going to just assume that in order to have a non-trivial problem, that you know this constant is not 0. So then we can cut it. We do the algebra, okay, blah, blah, okay. And then we're going to end up with an equation in G, right? So we end up with something that will look like this, G prime of, you can even see directly if you're more comfortable with calculations. So G prime, so this is the left-hand side, and then we do the mumbo jumbo, what we have to do, and we end up with minus a half here, x over root dt, g second in x over root dt. And I do advise you to do all these dots that I'm leaving, you know, like complete the calculation, okay? So the algebra, whatever. And you can see now the little miracle that is happening, okay? So if, when I'm looking at this these expressions, okay, the argument here is x over root dt in the three things. So actually, I could just call this x over root dt with a letter. So let's say I'm doing, let's call it s. And then with this notation, what I get the equation that, an equation, an ODE that is looking something like this. And that's beautiful. But it's an ODE. And actually it's a simple ODE even, you know, it's not even a complicated one. So we reduce this, this PDE, most of you didn't do the PDE course yet, right? You know, to something that is intro ODEs. Okay, so let's solve. Let's see. So I'm gonna flip the page again. Okay, so here let's write what S is, do not forget, because we're gonna come back to it. Okay, and we ended up with this equation, G prime of S is minus a half S G second of S. Okay, so I'm gonna denote by G of S, the G prime of S, the big one, the capital one, capital letter one. So now we can substitute. Okay, so we end up with right, okay, so here is backwards, right? There you go. So this is G second, there, G second, and there's G prime. Good. So please correct it. So the algebra is backwards here. Okay. And so here, yeah, okay. There you go. Okay, did you correct it? I'll write it nicely. I'm trying to fit more into the lecture. That's why I'm a bit sloppy here. And I just, because if I would do it, then it would be better, right? If we would do it together. Okay. All right. So did you correct it? I hope so. I'm going to flip the page back here. Okay, there you go, G prime. So now we end up with this ODE. You see? Oh, what did I write here? What am I writing here? S over 2, right? There. Good. All right. Okay, and this is a separable ODE, right? So this is nothing else but dg ds equals minus s over 2g, which is dg over s is minus a half, dg over g is minus a half s ds, okay? And again, I'm gonna let you integrate, right? So you're gonna put the integral sign here, blah, blah. Okay, please check your intro ODE course or the last lectures in Calculus 1. Okay, so you end up with G of S equals C1 E at minus S squared over 4. Okay, so that's the derivative of the big G. I'm trying to finish this problem, you know, to not let it be just like that, okay? It's nice because I could just stop like, oh, we just reduce it from 5 variables to 2, but actually we can do even more. All right, so now we remember what little g of s is, so we put it in, right? So we have that g prime of s is c1 e at minus s squared over 4. So if we integrate, right, we have, this would be c1 integral, right? I just want to make sure that I'm not writing 0 to s of e at minus sigma squared over 4 d sigma plus a c2. Okay, so I integrate it again. Now I don't know what is, I missed the D on the way. They're saying, okay, what is the D? Right, so there is a D here, right, okay, right, okay, that is good, good catch. So then this D cuts with this one as well, but we still have one left from here, so it's okay. Good, thank you. Alrighty, so we keep going. So it doesn't change anything on the way, it's just the D that was cut there. Good. Okay, so now we have to, okay, we go back to the equation. So we knew that u of x and t, right, was, where is it? Where is it? Where is it? Where is it? U of x and t. Where did I put it? There you go. U naught g of x over root dt. Okay, in a, where s is this guy, right? So g of s if you want, right? So there you go. So now what I'm going to do, in other words, from these two guys, we end up with u of x and t equals u naught times c1 integral from 0 to x over root dt e at minus sigma squared over 4d sigma plus c2. Okay, I should breathe for a second so you catch up, I guess. Good. Okay. So now I remember the initial condition. So we had 2 was that u in 0 and t is u naught. So when I'm putting them together, right? So here, this one and this one, okay? It gives me that u in 0 and t, which has to be u naught, is also u naught plus c, right? C2, actually. From where I'm getting immediately, right? So in a sense, I shouldn't write this here, right? So it's just the right-hand sides of each one, like to be, you know. So that's the right-hand side of one, right-hand side of the other one, right? We're doing x equals 0, so this guy will disappear, and the integral term disappears. So that's why we get just u naught equals u naught plus, oh, it's not u naught times c2, not plus c2. Okay, u naught times c2. Okay. Right. So C2, because u naught is not 0, will be 1. Yeah. Yeah. So once again, you know, so I substituted what u is, right? So I get this expression with 2 constants in it, but then I remember condition 2 is one of the initial conditions, that when x is 0, u is u naught. Okay, so that's exactly what I put in. So equating the right-hand sides, right? We're making x equals 0 here. So this integral term becomes integral from 0 to 0. So it dies. So what we're having from all this expression on the right here is just u naught times c2, and that's what I wrote here. And it has to be equal to u naught. Now, because u naught is not 0, we can cut it. So we end up with C2 is 1. That's that. So now I'm going to flip the page. So for now, we have an expression of u of x and t equals u naught times some constant c1 integral 0 to x over root dt e at minus sigma squared over 2 over 4, right? It was over 4. D sigma plus 1. And we used the original ODE and we used one of the boundary conditions, right? One of the boundary conditions. So now we're going to use the second boundary condition that tells us something like this. So in other words, right, we will have that C1 integral from 0 to infinity e at minus sigma squared over 4 d sigma. Okay, so we'll have a u naught in front, plus 1 equals 0. Yeah. Yeah. There you go. And again, you know, because u1 is not 0, u0 is not 0, right? So I won't put it there, but anyhow, that's the idea, that we can cut it. We basically end up with C1 integral from 0 to infinity e at minus sigma squared over 4 the sigma plus 1 is 0. Okay. And now those of you who took well, I assume it's done in calculus 2 because it's a funky integral. It's also done, it should be done big time in probability. The thing is that and sometimes it's done in PDEs, like, you know, I did it last term in the PDE course, just, you know, to make sure that people know it. There is a fundamental integral that formula that can be computed that tells us that integral 0 to infinity of e at minus ax squared dx is actually a half root of pi over a. Okay, so this is a formula that we know. Okay, so that's what I'm going to use there. You know, those who took PDEs with me last term, you know, might remember that I told you, oh, that's the important formula. I even put it on a test. Okay, it was a quiz or something. Okay, so now I'm going to use this formula here, and together, all together now, okay, we're going to end up with, so all this term here becomes root pi, so we're going to end up with C1 root pi plus 1 equals 0, okay? So, you know, in this case, A is 1 over 4, right? So from where we get that C1 is minus 1 over root pi. And so, substituting now what is C1, we can write the solution to be, after we arrange it a little bit to look nicer, okay? Okay, e at minus sigma square over 4 d sigma, which is an interesting conclusion because we actually managed to solve that original question without knowing any PDE theory, right? So this is a very special example. There is a hidden symmetry, scaling symmetry in the problem, but there you go. You know, in this original question that we had, here is this, where it is, it's here, right? Here is this PDE problem, the diffusion PDE problem, okay? In which, you know, it's a problem with boundary conditions at infinity, right? So it's a pure PDE problem, you wouldn't expect to know how to solve it, but using dimensional analysis, we managed to reduce it to a problem in ODEs that actually can be integrated. And here is the solution. Nice.